14 from there. Is there any questions on any of that? Josh?
Do you do number 11?
Sure. Okay. So number 11. So on these simplifying problems, the first thing that I tend to look for is something algebraic to do. On this problem, when I go and I do that, I see that I already have one fraction, so there's no common denominator to make. In the numerator, there's no factoring to do because there's no greatest common factor amongst the terms in the numerator. There's no quadratic factoring to do because we just have sums and squares. So I don't think there's any algebraic thing to do here. So what I'm going to do now is I'm going to move on and look for an identity to use. I notice that I have a sine squared plus a cosine squared in the numerator. So I'm going to use the first Pythagorean identity that says sine squared plus cosine squared is equal to 1. Okay with that, Josh? Okay. Next, I'm going to look at this. Again, nothing algebraic to do, right? There's no reducing to do. We already have one fraction. There's no common terms. There's no like terms. There's nothing I can really, no factoring I can do with this because, again, it's a sum. So let's go to the identities. If I look at Pythagorean identity number 3, I see that 1 plus tangent squared is equal to secant squared. So that's what I would use here. And now if I go to look for something algebraic to do, I see that this is a fraction I can reduce. Right? If I have a secant squared on top and a secant on bottom, I can just reduce that down to be like a secant to the first. Is that okay?
Yeah.
Are you sure?
Are these identities all in our notes?
Yeah, so they're in the notes, and I compiled them all together onto the basic identity sheet. So they're all in one place, typed out nice and neat.
We don't have to memorize these today.
Not on this test. Eventually, you should have this sheet memorized, but not right now. It'll happen naturally, Margot. Don't panic.
So like that's a next semester thing, or like this?
I'd have to look at what we do a second round of identities at some point. At that point, these ones become prior knowledge, and you'd get the new set of identities on for that test, and this round of identities becomes things that are like we expect us to still have. But in all reality, if you've gone ahead and done this homework, you really find that there's only a handful of these that you really end up using over and over and over again. It's not like all of them are equally important. As you get a chance to use these things, you're going to be like, okay, so like I don't really ever use, these ones or those ones. And it's like, I kind of know them, but I don't really know them, and that's probably okay. Josh?
Oh, I was going to ask, like, which ones do you think are most important?
Well, we'll talk about that at a later date together as a group after you've had a chance to like do some practice and develop some intuition. You know what I mean? Yeah. I don't want to spoil it for you. Allie?
One.
Sure. Okay, so it says find sine if cosine is equal to 1/4 and tangent is negative. So I'm going to start with my Pythagorean, because that's a relationship that relates sine to cosine. Okay with that? So when I solve for sine theta here, 1/4 squared is 1/16. I subtract 1/16 from both sides to give me sine squared equals 15/16. And when I square root both sides, I have plus or minus square root 15 over square root 16, or really just 4. So far, so good, Allie?
Yeah.
Okay. Now, I know that tangent is sine over cosine. So I know plus or minus square root 15/4 divided by positive 1/4 has to be negative. Well, what does that force the plus or minus to have to be? Negative. Yep. So there's my answer. Is that okay with you?
Yep.
So my answer is negative root 15/4. Margot?
Number 5.
Sure. So I'm going to start with the Pythagorean here. So I have 1 plus cotangent squared is equal to cosecant squared. So let's see, that's 25/81 plus 81/81 is 106/81. And we'll square root both sides there, so plus or minus square root of 106/9. Oh, shoot, I misread the question here. This is, I retract what I want to do here. Is that okay?
Okay.
Since it says all 6 trig functions, I'm going to go about this a different way because it'll probably be a little bit easier. Let me think. Well, maybe not. That's fine. We'll do that. We'll do this. I know since sine is negative, cosecant has to be negative as well. So there's 1. And then 1 over cosecant has to be sine, correct? And you should probably rationalize that denominator. I'm just going to elect not to do that right now. That's okay?
Yeah.
And then I know cotangent oh, come on, pen. There we go. Okay. So I know cotangent is cosine over sine, right? So I know that if I multiply both sides by sine, cosine is going to be sine times cotangent. So that's going to give me 5 over root 106, which again, rationalize that denominator. So secant is going to be the reciprocal of that, right? And then the easiest one of all was tangent because, well, that's just the reciprocal of cotangent. And I think that's all of them now, right?
Yeah.
Yeep. Taylor.
Can you do number 8?
Sure. So I notice algebraically right away, I can reduce the fraction. And at the same time, I'm going to use my cofunction identity that says the complementary angle or tangent of the tangent is equal to cosine of the complement. I'm sorry, cotangent of the. Anyways, I'm using the cofunction identity to get to here. Is that okay, Taylor? So I'm looking at this one. Okay. And I'm going to think about this as two fractions multiplied to one another. And really the only reason I want to do that is because I'm going to turn cotangent into cosecant over secant using quotient identity 3. So again, that allows me to reduce. So I have 1 over secant, which using the reciprocal identity is just cosine. Is that okay? At this spot, you could have maybe turned those both in terms of sine, written them both in terms of sines and cosines. That would be okay to do also. I wasn't sure where this was going to go. That might have been a little, like, one step quicker. Because you would have been left with 1, or just cosine at the end instead of 1 over secant. But, whatever. Okay. Anybody else here on this assignment? Luke. Sure. So secant we could basically get for free, right? That's reciprocal of cosine. Then I'll use the Pythagorean. So I know that sine squared plus cosine squared is equal to 1. 3/4 squared is 9 over 16. When I subtract that from both sides, I get 7 over 16. When I square root both sides, that's going to be plus or minus root 7 over 4. Okay with that? Now I can tell which one is positive and negative. I know that cotangent is cosine over sine. And if cosine is positive and cotangent is negative, sine had to be if cotangent is cosine over sine, and cosine is positive, but cotangent is negative, what does that say about sine? It also has to be negative. Oh, hold on. My pen decided to stop working. Okay. I need to do this real quick. Oops. Okay. So we said that this has to be negative. And once we have that, we get cosecant, like almost immediately from that. Now really you should be rationalizing that denominator. I'm not going to bother to do that right now. Is that okay? So there's sine and cosecant. We have cosine and secant. The last things we need are cotangent and tangent. So tangent is sine over cosine. So that becomes negative root 7 over 3. And cotangent is the reciprocal, so negative 3 over root 7. Again, rationalize the denominator there, but is that okay?
Yeah.
Sure. So it's usually just the first one that's kind of the tricky one to get. From there, just kind of like, you're just basically using the reciprocal or quotients to get all the rest of them. Okay. So let's talk about section 5.2 then. So last chapter, we did things that looked like this, right? Find the exact value of sine inverse of 1/2. Right, you guys remember doing this just a little bit ago? To do this, you go and I know the fundamental range for sine is negative pi over 2 to positive pi over 2. So if I go to my unit circle and locate where y is equal to 1/2 in quadrant 1, that gets me my answer, right? There's just one answer. What if we instead ask for to solve sine x equals 1/2? How many answers does this have? More than 2. Infinitely many. So if you think about this from a graphical perspective, right, the graph of sine kind of looks like this over and over and over again, right? 1/2 is like here. You're going to get infinitely many solutions on that, right? Is everybody okay with that? Just thinking about it from a graphical perspective? So IMS is just infinitely many solutions as a descriptor or as an abbreviation. But how? Well, that's true. There are infinitely many solutions. Can we describe what those solutions are? Because that doesn't mean that any value for x is going to be a solution, right? There's a difference between all real numbers as a solution and infinitely many solutions. You guys agree with that? So if I wanted to solve this, we do go and do sine inverse of 1/2, but we're going to ignore the range of sine inverse. We're going to go to the unit circle and find all the locations where y is equal to 1/2. So that's at pi over 6 as well as 5 pi over 6. So inside of one period, actually on the unit circle, we've located those two solutions, right? Everybody agree with that? So how far apart should these two solutions be? They're going to be one period apart, right? Everybody agree with that? Similarly, between these two solutions, also one period, right? How far apart are going to be those corresponding solutions always? One period, right? Everybody agree? So what we're going to say then is our solution is pi over 6 plus 2 pi k, where k is any integer value. So that what we're saying is pi over 6 is a solution, and then any angle coterminal to pi over 6 is also a solution. That's what the plus 2 pi k, where k is an integer, is representing. Is if you're adding or subtracting any multiple of 2 pi, you can get another solution. Is everybody okay with that idea? And then we can do the same thing for 5 pi over 6. John?
You said pi over 6 plus pi k, where k is number of integers. Wouldn't that cover both?
No, because pi and 5 pi over 6 are 4/6 of a pi apart, not one full pi apart. Right? Now, there could be situations where that you can do something like that and kind of combine both solutions into one, but there's a lot of solutions or situations where you can't. This is one where you can't. Okay. What if we instead asked us to solve this for x's between 0 and 2 pi? So the same problem, we're just now asking to solve it between 0 and 2 pi. Well, we just go to the unit circle, because that represents all the angles between 0 and 2 pi, or only represents angles between 0 and 2 pi, and then just pull the two values, right? What if instead we had asked you to solve for, I don't know, something on this interval, from negative 5 pi over 2 to 11 pi over 2. Well, what I would do in this case is I'm going to take our infinitely many solutions and use those solutions to generate the answers between negative pi over 2 and 5 pi over 2. So if I add 2, or if I, clearly pi over 6 is in there, right? Everybody agree with that? If I add 2 pi to that, I get 13 pi over 6. That's like 2 and 1/6, right? That's smaller than 11 pi over 2, or 5.5 pi. So that one will work. If I add 2 pi again, I get 25 pi over 6. That's like, what is that? Like 4 1/6. That's still less than 5.5 pi. If I add 2 pi again, I end up with 37 pi over 6, which is a little bit more than 6 pi. That's too big. Right? That's bigger than 11 pi over 2. But I can also have negatives, so I should subtract as well. So if I do pi over 6 minus 2 pi, that gives me negative 11 pi over 6. So that's like negative 1 5/6. That's still bigger than negative 5 pi over 2, right? Negative 5 pi over 2 is like negative 2.5. This is a little less than negative 2, or a little more than negative 2, I guess, since it's negatives. But I try it again. So I subtract another 2 pi. That'll give me negative 23 pi over 6. But that's too small now, right? That's definitely less than negative 2.5 pi. That's almost negative 4 pi. So we'll cross that one out. So we found all the solutions between negative 5 pi over 2 and 11 pi over 2 that can be coterminal to pi over 6. We'll do the same thing now for 5 pi over 6. So 5 pi over 6, add 2 pi. That's good, little less than 3 pi. That's still fine. I add 2 pi again. That is still less than 5 pi. So that's good. But if I add another 2 pi to that, that's almost to 7 pi. That's too big, right? Has to be less than 5.5 pi. Is everybody okay with how I'm doing this? But we also have to worry about the negatives, so we'll subtract 2 pi now. So negative 7 pi over 6, that's good. And if I do another one, that's going to be negative 19 pi over 6. That's a little bit more than negative 3 pi. That's too small, though, right? So those are going to be my 8 solutions. So if I have a weird interval that I'm solving over, I don't try to solve over that interval, really. I'm going to find the all real numbers solution and just use that solution to keep finding angles that are coterminal, and I'll keep going up or down until I find something that's outside of my range. Does that feel okay? So it's really still the same problem as the first one. We just have this like extra little guess and check piece at the end, which is not too bad because it's pretty easy guess and check. You're just adding and subtracting 2 pi's until it doesn't work. What do you guys think? Is this okay? Let's do some more examples. Okay? So let's say we want to solve cosine squared x equals 1 on the interval from 0 to 2 pi. Notice that we have a bracket at 0 but a parenthesis at 2 pi. Again, what do the brackets and parentheses mean again? The bracket means that number could be included in the set. So 0 is an answer that this problem can have. 2 pi would mean that number is not included in the set. So 2 pi is not an answer that we could have for this problem. Everybody remember that? Okay. So, first things first, what would you want to do first on something like this? Can I do the inverse to both sides? No. Why not? Because I have that squared on there, right? So we got to do something about that squared. What do you want to do to get rid of the squared there on the cosine? You could square root both sides. That's fine. That's probably the obvious thing to do. Okay. So when we square root both sides of an equation, what happens? What do we have to remember? Plus or minus. Everybody's okay with that? So this is really going to break up into 2 separate equations. So I may have cosine x equals 1 and cosine x equals negative 1. Everybody's okay with that? So cosine inverse of 1, I'll go to my unit circle. And I'm going to look for where the x coordinate is 1. That happens only when our angle is either 0 or 2 pi. It's the far, it's the positive x-axis is where the x-coordinate is 0. Right? So right when we start, the x-coordinate is 1. And then again at the very end, the x-coordinate is 1. Everybody's okay with that? Do we need to pull up the unit circle and show you? Or you can remember it in your head? We good? Okay. But remember, 2 pi is not in our feasible solution, so I'm not going to write that down. I'm just going to write 0. So the other equation then, again, we do the cosine inverse of both sides. So then I'm going to go to my unit circle and look where the x-coordinate is -1. That happens only at pi. That's on the negative x-axis. So those are my two solutions. Now, John, if this was a situation where we were looking for, instead of all real numbers, instead of from 0 to 2 pi, we were looking at all real numbers, we might have written down x is equal to 0 plus 2 pi k. Oops. And then x is equal to pi plus 2 pi k. And there you notice that the distance between the coterminals everywhere is pi, right? So this is a case where you could combine these together and just say 0 plus, come on, pen. My pen just stopped working. Come on. Come on, you stupid thing. All right, we're going to do this. We're going to unscrew the cap and take the battery out for a second. And then screw it back on. This is like the restart your computer fix for your pen. And that did it. Technology is wonderful. So there's a situation like John was mentioning, like, hey, can sometimes we combine these two solutions into one representation like this? That's a situation where that could happen. So speaking on this sort of situation, if you looked at my answer keys, this would be how I would represent my answer on the answer key. I wouldn't mark it wrong if you did not do that on the test. Just FYI. So if you left these as two separate answers instead of combining it into one answer, that's still okay. I wouldn't mark that wrong. But just so you know, on the answer keys everywhere, I'm going to do this because it's way less writing. But it's not a requirement. It's still representing the same solution sets. Okay? Let's do some more, right? This is all new. This is potentially quite challenging. Let's do another. Oh. So let's say we have 2 cosine squared x plus cosine x minus 1 equal to 0. And we're solving this again from 0 to 2 pi. Eep! This looks confusing. Anybody with an idea here? Okay, you want to try factoring out a cosine x. The problem with that, though, is that that's not a common term to everything, or not a common factor to all the terms. What if instead this was just like 2a squared plus a minus 1 is equal to 0? If we wrote it like that, would you know what to do? Yeah? What would you do if it was just 2a squared plus a minus 1 equals 0? And you wanted to solve that equation. This should be something that's super familiar. We spent a lot of time last year doing these sorts of problems. What kind of an equation is this called? It's a name. Quadratic. Great. What are the two best ways to solve a quadratic equation? Factoring or the quadratic formula. In this case, which one would you think is going to be more appropriate? I mean, I'd factor this, guys, right? If this has an exact answer, if we're looking these things off the unit circle, this best be factorable. Could I use the quadratic formula still? Sure, it's not wrong to do that. I'm going to factor it, though. It's going to be my choice. Mostly because it provides an opportunity to review factoring with us. Yeah. So, to factor a quadratic, the method's different if the leading coefficient is 1 or if the leading coefficient is not 1. In this case, what's the leading coefficient? 2. That's not 1, right? This means that we're going to have to do the long version for the factoring. So what I'm going to do is I'm going to look for two numbers that multiply to give me the leading coefficient times the constant term. And then those same two numbers need to add to give me the linear term's coefficient. So what two numbers multiply to give us -2 and add to give us +1? 2 and -1. Everybody agree with that? Now that doesn't allow us to go straight to our answer. What that gives us is a way to replace the coefficients on the linear term. So notice that I've replaced a with 2a plus -1a. Still equals a, right? The reason I want to do that is because I'm going to make two groups. From the first group, I'm going to take out the greatest common factor of 2a. When I take out the 2a, what's left? A plus 1, very good. And from the second group, greatest common factor is -1. When I take that -1 out, what's left? A plus 1. Notice now each of these terms has an a plus 1 in common. So if I factor out that a plus 1, I'm left with 2a minus 1. Now it's factored. So if we go back to our original problem, notice that I just had replaced my cosine x's with a's, right? So if we go back here, we're going to have cosine x plus 1 times 2 cosine x minus 1 equal to 0. Is everybody still on board? I apply the zero product property that allows me to set each of these factors equal to 0 and solve them separately. Everybody's okay there? So for the first one, we're going to subtract 1 from both sides and then do the cosine inverse. So I go to the unit circle and I look at where x is equal to -1. That happens at pi. Everybody okay with that? In my second equation, I'm going to add 1 to both sides, divide both sides by 2, do the cosine inverse. Then I'm going to go to the unit circle and look at where the x-coordinate is 1/2. That is pi over 3, and then 5 pi over 3. And we're all okay with how I'm going to the unit circle and pulling these things, right? I have this stuff memorized, so I don't have to look at the unit circle. You probably would look at the unit circle. I don't imagine that you'd have this all memorized. If you do, that's fine. If you don't, not an expectation that you ever would. Any test you'd ever have to use the unit circle, I will give you a unit circle. You're at no point in time expected to have it memorized. Are we doing okay, though? So that one was a bit more challenging, but the trigonometry part, really no more challenging than the first problems we did, right? What was the hard part? Was the algebra, right? Let's do another. Here, the trigonometry part's going to be sneaky. The algebra part, not so bad. What do you notice that's different about this problem than any of the previous things that we've seen? Yeah, we have a coefficient attached to the variable inside of our trig function, right? That's going to be your cue that what we're about to see happen is we have to be careful about these situations. So there's some additional stuff that we need to do. So naively, you'd think, okay, well, 2x is equal to sine inverse of 1. And the sine inverse of 1, if I go to the unit circle, I look at where the y-coordinate is 1. That happens only at pi over 2. And then I just multiply both sides by half, or I divide by 2. And I'd say my answer should just be pi over 4, right? That all makes sense to everybody? Yeah, why is that not right? That's exactly what we've done before, right? What's the problem with this one? Anybody with an idea? So if we go all the way back to like when we talked about the graphing, oops. This is what the 2 is, right? It's a b coefficient. What does that b coefficient change? Of course. What does the b coefficient change with the graph? Oh, guys. Okay, so horizontal dilation. So that affects the period, right? So what if the period gets smaller? Could we have more than one answer inside of 0 to 2 pi? Oh, yeah. So that's the issue here. So let me show you the easiest way to kind of deal with this that makes it kind of dummy proof. So we'd approach this the same way. We go to the unit circle, retrieve where the y coordinate is 1. But instead of just writing this as pi over 2 plus, or 2x is equal to pi over 2, we're going to write this as the infinite solution. I'm going to include the plus 2 pi k. Everybody's okay with that? Everything is the same except I'm including this plus 2 pi k. Let me do that for us. That's probably starting to get a little messy. Yeah. So when I divide both sides by 2, this becomes pi over 4, but this becomes pi k, right? When I divide that by 2. And now I'm just going to take my base answer, which is pi over 4, and I'm going to keep adding or subtracting pi from that until I get things that are outside or inside of, or until I get things that are outside of my interval. Right? So if I subtract pi, clearly I get something negative. I don't want that. Everybody agree? If I add 1 pi, I get 5 pi over 4. That's still okay. If I add pi again, I get 9 pi over 4. That's too big. So we'll discard that one. So this piece is the trick to dealing with that. If I have a coefficient on my x, have to really worry about doing this. Let's do another example where this happens. Sound good? Because this is kind of sneaky, right? Like, ooh, I would not have thought about that. All right. Oh, let's, again, 0 to 2 pi. All right, what do we want to do first? Oh, I don't mean this to equal 1/2. Sorry about that. What should we do first? Square root both sides. When we do that, what do we get? Or what do we have to remember, I should say? Plus or minus. And the square root of 1/2 is really root 2 over 2, right? I rationalize the denominator there. If you don't see that, we can do it by hand, but I think at this point we've run into enough rationalizing of these things to see where they kind of see that. Okay. So we'll do the cosine inverse then. Oh, we split this into 2 equations, really. Right? One with the positive and one with the negative. Then we do the cosine inverse. Again, if I'm going too fast on something, or if you're not quite sure, please stop and ask.
How did you get from a half to 2 over 2?
So the square root of 1/2 is the square root of 1 over the square root of 2. And then I rationalize the denominator.
Oh,
Cool? Okay. So once we have this, now we're going to go to the unit circle. I'm going to look where the x-coordinate is root 2 over 2. So that happens at pi over 4. And it happens also at 7 pi over 4. And here we're going to go to the unit circle and look for where the x-coordinate is negative root 2 over 2. So that happens at 3 pi over 4. And also at 5 pi over 4. Yes.
Is it always going to be on the unit circle, or do you
So we haven't done an example where it hasn't been. So the answer is no, it won't always be. In the beginning, we're going to do it that way to kind of like keep the problem from getting like overwhelming. So we'll start with situations where everything is on the unit circle, but that will not always be the case. And it need not be the case. We know enough to be able to deal with it, but it's like you're taking like the hardest problem from last chapter and tacking it onto this problem, which is like not where I want to start, right? So we're just going to be, for right now, we're pulling things from the unit circle. Is that okay?
Yeah.
Okay. All right. Let's keep on rolling here. All right. So then we divide both sides by 3. So I get pi over 12 plus 2/3 pi k. And then I have 7 pi over 12 plus 2/3 pi k. And then I have 3 pi over 12, but really that reduces down to just pi over 4, right? Is everybody okay with that reducing that I did there? And then 5 pi over 12 plus 2/3 pi k. All right. So pi over 12, that's my base solution, right? If I subtract 2/3 of pi from that, I'm going to get a negative, which is no good because my interval I'm solving over is 0 to 2 pi, so I don't want any negatives. So I only have to worry about adding. If I add 2/3 to that, I get 2/3 is going to be like 8/12 with a common denominator. Everybody's okay with that? So I'd have 9/12 pi. I can reduce that, but I'm going to leave it not reduced for now because we'll make it a little bit easier later on to deal with just having like answers where I can see what's going on. And that's good. That's in between. That's still less than 2 pi. Add another 8/12 pi. That's still good, still less than 2 pi. If I add another, though, it's too big. Everybody agree? One more is going to be 25 pi. over 12, which is bigger than 2 pi. Ellie?
Can you just explain how you know to add the 2/3 pi? Yeah, how do you, yeah.
Oh, okay, so I divided both sides by 3. So when I divide this by 3, I have 2/3 pi.
Okay, thank you.
No problem. Okay, on to the next one then. So again, 7 pi over 12 is my base solution. I know if I subtract 8/12 from that, I'm going to get a negative. I don't want that. So we'll just be adding. So I get 15 pi over 12. That's okay. And I add another 8/12, and that gives me 23 pi over 12. That's still good. But if I add another, way too big, right? I'm already almost to 2 pi there. If I add another 8/12, I'm way over. Okay. Over here. So actually, maybe this makes more sense for me not to have reduced that. Let's leave that as 3 pi over 12. Again, because I'm going to be adding 8/12 everywhere. Probably just makes it a little bit easier to do that. If I add another 8/12, that's going to be 27 pi over 12. Too big. And then, let's see, 13 pi over 12. And then 21 pi over 12. And then too big. So those are going to be my answers. Again, if I was doing this, if you're looking at your test or your key, you're probably going to have things reduced when possible. So like some of this stuff would be reduced, but like I'm not going to worry about that right now in the example. You know what I mean? Those fractions can all reduce. If you looked at the answer key, they would be reduced. If this, I wouldn't worry about it until I'm done with this part, because it just makes the arithmetic kind of a pain to reduce along the way, since you're using the previous answer to just kind of add from. Just makes finding the common denominator and everything like a bigger pain in the tuchus the next time. All right. Let's do another. Okay. So, tangent 2x times sine squared 1/2 x equals tangent 2x. Yikes. Where do I start with this thing? Jackson? So that seems like a good idea, right? Makes this problem enormously simple, or enormously simpler. What's the problem with doing that? What are you potentially dividing by here? 0, because there's a variable in there, right? Tangent can be 0. So it's possible in doing so, you're going to lose a whole boatload of solutions, which is the case of what would happen here. So we actually don't want to do that. Instead, what you'd want to do is to move everything onto one side. So I'm going to subtract the tan 2x from the right-hand side over to the left-hand side. Is everybody okay to there? Now what? Starts with an F. Factor. What can I factor? The tan 2x is the greatest common factor, right? So far, so good? Now what? I can apply the zero product property here and separate each of these factors into their own equation. So far, so good? Okay. So here, we're going to go for the unit circle. And remember where tangent is y over x. Wherever y over x is equal to 0, that's the same place as just where y is 0. Everybody agree with that? So we have 2x equals 0 plus 2 pi k. And pi plus 2 pi k. Now I would, in this case, I noticed that these could be condensed. Which is going to make life way easier to have one equation to deal with rather than two. Because we still need to do some work on that. So everybody see that though? The first equation is saying 0, 2 pi, 4 pi, 6 pi. The second equation is saying 1 pi, 3 pi, 5 pi, 7 pi. If you combine all those together, it's really just 0 plus 1 pi, 2 pi, 3 pi, 4 pi, 5. Just going up by 1 pi's. So I can just combine them together into one. So if I divide both sides by 2 then, actually let's just call that, write that as pi over 2 instead of 1/2 pi. So 0 is our base solution. If I subtract 1/2 pi, it's negative. My answers are between 0 and 2 pi, so I don't want that. So if I add 1/2 pi, add another half, add another half, add another half, I'm at 2 pi, but that's actually too big because remember my interval is going to 0 to 2 pi, but the parenthesis is on 2 pi. So that's not a solution I need to include or should include. So that's halfway. We still have sine squared of 1/2 x equals or minus 1 equals 0. Oh my goodness, Mr. Kulik, are you kidding me? No. So we'll add 1 to both sides. Square root both sides. Remembering the plus or minus, that generates 2 equations. Go to the unit circle where y is equal to 1. That happens at pi over 2. And go to the unit circle where y equals -1. That happens at 3 pi over 2. Oops. Oh my goodness. Sorry, those of you listening at home on the recording. That was probably scary. Multiply both sides by 2. And actually, from right here, I can tell that, well, we'll write it out anyways. That's fine. So my base answer here is pi. If I subtract 4 pi from this, I get something negative. Definitely don't want that. If I add 4 pi to this, definitely too big. So that's the only solution there. But notice that it's actually already on that list. So I'm just going to discard it altogether, because I don't need to write it more than once. Everybody's okay there? Similarly, here, my base solution is 3 pi. That's too big altogether. So there's nothing from that list either. So my only solutions are these guys right here. Holy shamoles. So at this point, we should be pretty comfortable doing this. So you guys can work on 15 to 46 is the solving part for the problem set. It is. Hold on, because it gets worse. Each of those problems has 4 parts to them. So there's a solving from 0 to 2 pi, all solutions, and then from 2 goofy intervals. Keep in mind, though, does that really 4 different problems? Not really, right? Once you have your answers from 0 to 2 pi, it's easy to write the infinite answers, right? Because you just slap the 2 pi k's on at the end. Once you have that, if I'm asking you to solve over a weird interval, you're just basically doing the 2 pi k's until you get stuff either to not in that interval. So once you have the solving part done, you don't really have to resolve for those other ones. You just have to like go a little further, go a little further, go a little further. This week, what should you be expecting to see at some point this week? That's a good bet.
What day though?
I don't want to tell you because I'm afraid people will skip.
Well, Friday. Oh, let's do it.
Yeah, just tell us, we won't.
Yeah, we won't. I promise.
I mean, didn't my answer right there just kind of tell you the day?
Oh no.
I mean, we can say anything.
Wait, what's up?
And just as a, we'll even say this. Oh, everybody's leaving on me. I would worry about just 5-1 for the homework questions. Okay.
Yeah, that's fine.
Have we assigned worksheet 1 yet? Worksheet 1 are solving problems, so no. I'm talking about section 5-1. So the problems that we talked about today at the start of class.
So like 1 through 14?
Yeah.